Hi everybody. So let's get started. It is my pleasure to introduce today's speaker, Naoko Sakaeda. Naoko got her PhD from the University of Albany working with Paul Roundy. She then went on to do a postdoc at NOAA Astral under collaboration with George Kalatis. And she is currently assistant professor at the University of Oklahoma. Naoko's interests are fairly broad in the topics of tropical meteorology. She's done research from multi-scale interactions ranging from the diurnal cycle of convection all the way up to the intraseasonal fluctuations with the MJO. And today she'll be talking about intraseasonal cloud organization, DYNAMO and AMIE field campaign. So without any further ado, Naoko, take it off.
Thank you so much for the introduction. Is the microphone working?
Yeah.
Yes. Okay. And then I want to make sure that I don't cover up my slides, so maybe I'll stay here. Thank you so much for this opportunity to share more of my work with you today and visit this department. I almost came here for my undergraduate degree, but I said it's going to be too cold for me. And so I went somewhere else. Because of the pandemic, I had not left the state of Oklahoma for over 2 years, so it's a very exciting opportunity for me to actually meet you all in person and get to talk about research. So what I'm going to talk about is the Intraseasonal Cloud Organization, and by intraseasonal, what I actually mean is the Madden-Julian Oscillation. And given how much work on the MJO is happening within this department, I thought maybe this is a slide that I didn't need it, but let's just go through it anyway. So the Madden-Julian Oscillation, as most of you are familiar with, is the dominant mode of intraseasonal circulation convection in the tropics. And this is a schematic illustration of the typical life cycle of the MJO. So oftentimes, where I indicated with blue is the enhanced region of convection associated with the rising motion on a large scale that spans over tens of thousands of kilometers. And that convection often grow over time as it slowly propagates eastward until it reaches the Central Pacific and decay. And this typical life cycle happens on the order of 40 to 50 days, therefore it has the intraseasonal timescale. And because of such an expansive area, this phenomena can impact the convection and circulation. Its impact is not limited to the tropics and extends beyond the tropics. Therefore, the MJO is known to be an important source of the subseasonal to seasonal predictability skill. And that's why we're interested in this phenomena. We can see this phenomena on the raw data. So this is longitude by time diagram of brightness temperature average around the equator, time going forward downward. So anything that moves to the right of this diagram with the time indicates eastward propagation. And people see the MJO here. Oh, nodding face. Okay, let me help you a little bit. So here I'm just kind of capturing the general suppressed and enhanced convective area that is associated with the MJO. With this kind of schematic, I hope you can now see this oscillating period of high and low brightness temperature associated with what we call suppressed and enhanced convective envelope of the MJO that slowly propagates eastward. And the state of the MJO has a significant impact on cloud development locally. So for example, this is an IR image of Indian Ocean during the suppressed phase of the MJO. So from this image, you can see that there's still clouds, but most of them are being isolated, and there's some deep convection, but there remains to be isolated and scattered around. And this is the state where we often refer to as unorganized, suppressed state of the convection. But as we move into about 20 days later, the state has changed dramatically once the enhanced envelope of the MJO developed. And this is now the same image over the same region, but during the enhanced convective envelope of the MJO. So you can now see the overall cloudness has expanded significantly, and you now see a much higher number of larger convective systems, including the mesoscale convective systems that are being active over this region. And this is the state where we often call organized or enhanced convective state of the MJO. And this organization or transition from unorganized to organized state of the convection is essentially an intrinsic part of MJO dynamics. This is a nice schematic from mHealth website that I stole, and he has a lot of nice schematics that I use all the time in my talk. And what this is illustrating is the transition of the cloud type associated with the development of enhanced convective envelope. And this demonstrates some of the coupling between the cloud transition and cloud development with the dynamics of the NJL. So for example, the development of the shallow convection could be driving the moistening of the atmosphere, leading to the development of deeper convection. At the same time, the latent heating and the radiative interaction of the clouds are part of the process that could help be driving the illustrated circulation of the NJL. So this kind of illustrates that the effect of cloud organization on the large-scale environment is an important component of the geodynamics that we remain to understand completely, and that's probably one of the challenges why we don't capture the MJL well in the numerical models. So the topic of today is trying to understand what leads to, how can we define, and what dynamics or mechanisms are associated with this transition from unorganized to organized state of the MJL. So now I repeatedly use the word cloud organization so far. If we want to understand cloud organization, we probably should know what it means. So how do you define cloud organization? Anybody want to share your thoughts? I saw this.
More than one cloud in a
More
short.
than one cloud. That's very interesting. Any other thoughts? Yes.
More than one cloud associated with the same divergence field.
Okay, more than one cloud associated with the same divergent field.
Spatial aggregation.
Spatial aggregation. These are all interesting answers. So when I thought about this question, I did not know the answer to this question myself. So I went around the field and asked different experts how they define cloud organization, just like I did now. Interestingly, I got a lot of different answers. One person said, well, tropical cyclone is the highest degree of cloud organization. Well, you probably can guess what this person studies. The other person said self-aggregation or aggregation. And this self-aggregation refers to a phenomenon that we often observe in idealized simulation with radiative convective equilibrium. And this is an example of figure showing this phenomenon. So from the left to the right of the figure, I hope you can all see that you can see that the clouds, this is showing the outgoing long-wave radiation. So you can see that there's clouds are aggregating into one cohesive area, and that's what's known as self-aggregation. The other person said it means it has some stratiform anvil clouds, or the formation of the mesoscale convective system itself is the organization. Okay, we kind of see that there's some consistency, that these people are not necessarily talking about completely different things, but the mechanism behind all the phenomena are completely different. Not maybe completely, but they are different. Something different to this is that another person said it is about something that is just not random. Or another person said it means one convective cell leads to the formation of another. So here's another example. So these last two people are not necessarily talking about the formation of a large system or the stratiform or mesoscale convective system. What they're interested in is the distribution of deep convective force. And that's kind of illustrated on the right figure. This is showing the contours are showing the location of the updraft. And in this paper, they state that this state demonstrates an organized state of convection. So, I think they're not all talking about completely different things again, but the precise definition matters, and this demonstrates that the word that we use commonly, cloud organization, actually has a very vague definition. So this motivated me to answer the question. Among all those definitions the other experts talk about, which of the existing definitions of cloud organization maybe best describe the transition of NJL suppressed to enhanced convection? Another question that I want to ask is how to observe cloud populations evolve from unorganized to organized state on intraseasonal timescale. Well, it gets kind of tricky when I say I want to understand organization when I say I don't know what organization means. So what I'm just going to assume that the intraseasonal enhanced convective envelope is what we often refer to as the organized state, and suppressed MJO convective envelope is the unorganized state. And we still rename that term as a vague term that generally indicates the state of the change in the state of clouds from suppressed to enhanced convective envelope. But what I'm trying to understand is how do clouds evolve from the suppressed to enhanced convective envelope of the MJO. So to do this first, I'm just going to use what's being out there. So the first step is to evaluate all these different kinds of cloud organizations that are out there to see which of these best represents the transition from MJO suppressed to enhanced convective envelope. And this should be 5. I can't count, I guess. So instead of kind of talking about the technical details of how these indices are defined, let me just briefly talk about what they attempt to measure. So the first two indices, simple cloud organization index sky and morphological index of convective aggregation Mika, same name as my daughter. These two indices attempt to measure what I call aggregation. And I define aggregation as the evolution toward a state with a smaller number of larger convective systems. So here's an illustrated example of going from less aggregated to more aggregated state. And these two indices are trying to measure this state. The third index, organization index, or called IORG, is trying to measure non-randomness. By non-randomness, it refers to a state where the distances between objects are closer than the distances expected for the same number and size of the object if they were distributed randomly. So as illustrated here, for the same number and size of clouds, if they were closer to each other than expected for a random distribution, that this index is going to measure as more non-random. The fourth index, convective organization potential, measures clustering. The clustering is a little bit different from non-randomness. Clustering just, I define it as a change in cloud population towards a state with decreased distances between them. So the difference between this and the non-randomness is that the clustering only cares about the physical distance between them, whether it's random or not. So here's an illustrated example from going to less clutter to more clutter. So just by increasing the number or size of the convection, you do get to naturally closer distance between them. So this state is getting more cluster, but not necessarily becoming less random. So that's the difference between the prior one and this one. The fifth one is named the radar organization metrics. This one, in addition to clustering, also considers size. So the authors of this index also assume that an organized state is assumed to have larger convective systems. So you can see that all these different indices are thinking about different parameters associated with clouds and defining what they define as cloud organization based on those parameters. So what I'm going to do is to calculate those cloud organization indices that I mentioned before using radar data that was deployed during DYNAMO AMIE field campaign. This was a field campaign that occurred over Indian Ocean from October 2011 to February 2012. Some of you were there, I think. And because the radar provides a high resolution in both spatial and temporal timescale that is continuously available for the period of the DYNAMO field campaign, it provides a very unique set of data sets that allows me to address my question. The other data that I'm going to use are CSU upper air and surface graded analysis to evaluate the environmental factors. And also I'm going to use NOAA-interpolated outgoing null radiation to define the state of the MJO. So, but the region that I'm going to focus on is right here where the SPOCA radar was deployed. So to identify the state of the MJO, so I first have to identify the state of the MJO where the SPOCA radar was deployed. I'm going to do that using the local state of the MJO, using the outgoing long-wave radiation anomalies that are filtered for the MJO wave number frequency that is average around the atoll where the radar was deployed. And that time series defines the horizontal axis of this diagram, and the vertical axis is defined by its time tendency. And on this diagram, the 0 degree with the negative OLR anomaly is defined as the enhanced state of the MJO. And the positive or 180 degrees with the positive OLR anomaly is defined as the suppressed phase of the MJO. And between around -80 with the negative tendency of the OLR anomalies is what I define as the growing phase, going from suppressed to enhanced, and the opposite side is defined as the decaying phase of the MJO. And using this diagram, I can plot anything. Oh, before I go into that, this is what it looked like during the DYNAMO event, where 3 separate MJO events were observed. So I will be analyzing these 3 events. So as I said before, I can plot anything with respect to this local phase of the MJO. And for example, this is showing the composite of the OLR anomalies itself. And by construction, the enhanced phase of the MJO, the 0 degree, should be associated with the negative OLR, and opposite scenario for the positive and negative 180 degrees. So I'll be using this MJO local phase throughout this talk. Also, to calculate the cloud organization index, I need to define some objects that are used to calculate cloud organization index, and that's when I'm going to use this radar data. Here's an example of the rain rate estimated from this radar on the left, and on the right is showing the rain type classification through the Powell et al. Algorithm. And the red indicates what's classified as the deep convection. And the blue is the stratiform, and the pink is the mixture of the deep convective and stratiform regions that is considered not being able to completely define as one or the other. And the other blue green region is the isolated convection. So I'm also interested in testing the sensitivity of cloud organization to different definition of this rain cluster. So one definition I'm going to apply, what I call the rain cluster, is defined as contiguous areas of raining points, including any rain type. So here's an example of rain cluster. So the shadow is showing the overall shape of each rainfall clusters. And this can be further subdivided to NCSs and something smaller, but I'm not going to get into the details of that. The other type that I'm going to define is deep convective clusters, and that is based on the contiguous areas of deep convective rain that is defined based on the Powell et al. Algorithm, and this is an example of the areas that are defined as convective rain clusters. And then I'm just going to track their number, size, and distance between them to calculate cloud organization indices that I defined before. Before going to that, let me first show you how the rainfall evolved during the DYNAMO. So this is, again, the x-axis is the MJO local phase, with the middle 0 degree is indicating enhanced phase. And the black line is showing the domain average rainfall from the radar. And then the red line is showing the rainfall contributed from the deep convective side. So you can see that the peak rainfall occurred slightly before the enhanced phase of the MJO, which was mostly contributed by the deep convective types. And let's first look at the 2 indices that are based on the self-aggregation. These are 2 indices that attempts to measure self-aggregation. What this is showing, again, so the black line is the aggregation, cloud organization indices that are calculated based on what I define as rain clusters. And the red line is the ones calculated based on the deep convective rain clusters. So both of these indices, what they're showing is that it's more aggregated during the suppressed phase of the MJO. So this suggests to me that the definition of aggregation does not seem to describe the evolution of MJO suppressed to enhanced phase, because it's saying that MJO enhanced phase is less aggregated. Let's look at the other index. So this is the index that attempts, yes?
Clarification question. Your previous slide, do you use like the centroid of your, you've identified clusters? Is it the centroid that you're using for all these indices, or is it that whole area that you've identified?
So it depends on, that depends on each organization indices.
Okay.
So I precisely follow their definition.
Okay.
Most of them, to measure distance between 2 rain clusters, they use the geometric centroid.
Okay.
But some prefers to use the distance between the edges of cloud.
Okay.
But that's all depends on the cloud
Okay.
definition of each index. So this is the index that attempts to measure non-randomness. So this index is more highly dependent on the type of rain clusters, and also it does not fluctuate greatly. But if you look at closely, the non-randomness seems to peak generally during the enhanced to decaying phase of the MJO. Another index, this is the one that measures clustering, and again, it kind of shows that it becomes more clustered during the enhanced to decaying phase of the MJO. And the last index is the Rome. This is considered size, no. So as expected, this is more dependent on how you define ring clusters. But this one shows that in general, again, the enhanced phase is associated with a larger size of ring clusters. So what did we learn so far? I kind of feel like I went through a lot, but didn't learn much about how the clouds actually organize, which is my main point, my first main point. So there are no consistent degree of intraseasonal organization that was diagnosed, and the cloud organization indices are not helpful to understand how clouds organize. And one thing that consistently appeared is that the indices based on self-aggregation does not seem to describe the state of MJO enhanced convection. So maybe self-aggregation is not something that can be applicable to the observed MJO. Other indices were also highly dependent on the definition of rain cluster. So these cloud organization indices could be very useful for some scenario, but if you're going to use it, I just recommend the users to be very aware of the underlying definition of cloud organization and the caveats associated with them. So because I didn't learn much, I need to revise my approach. Instead of all the looking at the cloud organization indices, it would be so much more helpful to look at the parameters that actually go into the cloud organization indices. And that's precisely what I'm going to do. I'm just going to focus on how those parameters of deep convective rain clusters evolve with the MJO. Those parameters that I'm going to look at are the number density, size, distance between them, non-randomness in their spatial distribution, and also their relationship with the development of stratiform rain. So here is now, again, the x-axis is the MJO local phase showing the number density of deep convective clusters. So you can see that their number density increases slightly before the enhanced convective envelope. So if you put more number of convective cores in the box, that should naturally lead to increased proximity, and that's what we also see here. This is showing the probability distribution of the distances between their nearest neighbors, and the block line on the left is showing the probability throughout the entire DYNAMO period. And then the shading is showing the probability conditioned by the local phase of the MJO after removing the probability over the entire DYNAMO region. So the red region, red shading, or positive anomalies in the probability indicates that the chance to get that nearest neighboring distance is higher for that particular phase of the MJO compared to the other time. So what this is showing is that, as expected, the distances between them are getting closer to one another as their number density is increasing. Here it's showing the similar plot for the size, the probability distribution of their size. And what this is showing is that after the number and the proximity increases, it is followed by the growth in size, perhaps maybe due to the merger of them, but that's not being proven. So here what this is showing so far is that from the enhanced to suppressed enhanced phase of the MJO, it starts with the increase in the number that naturally leads to a higher proximity of them, leading to the growth in their size. Another parameter that I haven't shown is the non-randomness, and this is a little bit more tricky to quantify. So I want to walk through how I do this. So here is showing the observed rainfall cluster example and showing its size distribution at the top and the distribution of their nearest neighbor distance at the bottom. What I'm going to do is I randomly shuffle the location of the observed rainfall clusters. So that's what's an example shown on the right. And just because I'm shuffling the location, it retains the same size and number information. But the distances between them will be randomized.
And I repeat this randomizing process for 100 times, which gives me some spread in the information of the expected random distribution. And that's what's shown at the bottom right. Now what I can do is compare the differences between these distribution of the observed versus randomized clusters to measure a degree of non-randomness. And that approach is actually similar to IOG index that I'm going to explain in a bit. But before I do that, let me show you the probability distribution of the distances of the observed and randomized convective clusters. The first point, the left is showing the observed, and then the right is showing the randomized. So you can see that in general, the shading is at the lower end of this diagram for the observed and random. So the first point is that the observed deep convection are rarely random. So they're non-random almost all the time. The other thing is that, as we expected, as the number of them increases, their distances naturally decreases, leading to higher probability of smaller nearest neighboring distance around the enhanced phase of that jail. So then to quantify the non-randomness, I follow the approach of the Tompkins and Samir, but in a slightly modified way. So what they do is they plot this cumulative distribution of the observed distances against the analytical solution of point distribution. And the point is that they use point distribution, which is not necessarily applicable as I've shown before, because their sizes can vary quite a bit. But what they do is, what they then do is that once they plot the analytical solutions to the observed cumulative distribution function, the area underneath this curve is defined as the IOR. And because assuming a point distribution is problematic, instead of using an analytical solution, I used the randomized distribution that was simulated through randomly distributing the observed rainbow cluster. So if things were completely random, the area underneath this curve should be 0.5. But if things are distributed more closer than expected for random distribution, the area underneath this curve should be greater than 0.5. So this gives us a measure of non-randomness. So higher than 0.5 means it's more non-random. So after calculating this, I can plot it on the NJ local phase space again. And then the top is showing the measure of the non-randomness. Interestingly, the peak non-randomness happens during kind of enhanced decaying phase of the NGL, when the number of them is actually decreasing. So that's interesting. Maybe what might be happening is that during that phase of the NGL, the isolated, let's suppose you have both isolated and clustered deep convective cores, but perhaps the isolated ones are preferentially being suppressed, or the formation of a new convective cell is restricted to occur within an existing one. And that would lead to decreasing the number at the same time, leading to more non-random distribution. So all of this evolution, I think, can be better understood by looking at this dimension that are formed by number density of deep convective rain cluster on the x-axis, and then their average nearest neighboring distance on the y-axis. So for each scan of the radar, I can quantify those two variables and then plot their distribution, which is shown in the shading here. First interesting point is that there seems to be a preferred distance between the two nearest neighboring convective cores. And that's about to be 5 to 10 kilometers. Why is it 5 to 10 kilometers will be a topic of another conversation, so I'm not going to expand into that. But we can also compare this to what would be expected if things were occurring randomly. So this blue line is showing the average expected nearest neighboring distance if the convective rain cluster was distributed randomly. So you can see that the distribution is generally fall underneath the blue line, which means that as you go increase the number of deep convection to the right, it does not happen randomly. Because if it does, then this distribution should be approximately following this blue line. So that's what I said. And that same point can be illustrated by looking at this degree of non-randomness. And that's what's shaded here. So So on this diagram, you can kind of interpret that for the same number of density, it becomes less random as you move to the bottom of this figure, meaning you're decreasing the distance between the convective cluster, and that might be an obvious one as illustrated in this case. Alternatively, if you can also be at the same distance between the two neighboring clusters, but it would indicate the state is less random as the number decreases. And so this is what's illustrated here when you have a smaller number of convective cells. To retain the same distance between them, that must indicate more or less non-random state. So we can also plot different things. For example, this is now showing the amount of stratiform rain conditioned by the number and the distance between the convective cores. You can generally see that the stratiform rain increases with the number of these convective rain clusters. Yes.
I'm sorry, I just had a question on your prior slide.
Yeah.
On the last one. Is there maybe like a quadratic sensitivity here that if those groups of 3 on the bottom panel there on the far left, they do look like groups of 3 that came from the prior one, but they might still be random, even though by the definition you're using, they're not. Is there another level that one would have to apply to get around that ambiguity?
Are you kind of thinking about if the process is random or not?
Yeah.
Okay, so this does not quantify anything about the process.
Oh, okay.
Yeah, this is just thinking about, given the distribution, should these be considered non-random or not?
Okay,
Yes,
okay.
if you compare these two,
Okay.
the bottom should be considered less random.
Okay, sorry.
Okay, no, I love the question. So where was I at? I explained this. Yeah, so the stratiform rain generally increases with the number of convective rain clusters, but there are also some interesting sensitivity to the distance between them as well. So what I wanted to do is kind of understand how the state of the clouds evolved in this dimension. So I can do that by looking at the probability of increasing trend in the number. So based on the present state that is defined by these 2 variables that define the x and y axis of this diagram, I can look at what's the chance that the next time step is going to lead to increase in the number of deep convection. So that's what's plotted here. The greater than 50% means that if you're at this particular grid point, that state wants to move towards to the right of this diagram. And if it's less than 50%, meaning that state wants to move to the left of this diagram. And similarly, this is showing the probability of increasing in the distance between them. So for this one, greater than 50% means that that state wants to move to the top of this diagram. If it's less than 50%, meaning that state refers to the bottom of this diagram. And you can plot that information as a vector here. And this kind of nicely shows how things evolve in this 2 dimension. To summarize, what I find is starting with a low number, more relatively randomly spread out deep convection, tends to rapidly increase in the number, and that naturally leads to a higher proximity and increased stratiform rain. But this doesn't necessarily happen in a non-random manner. But what then happens is that as the number decreases, it tends to retain similar proximity. So it's just going kind of horizontal to the left of this diagram, while the stratiform rain is decaying slowly. So this is actually very similar to the finding by the Cheng et al. 2018 paper, which they specifically looked at one rain date episode during the DYNAMO field campaign. And what they're showing here is that, kind of similar to what I showed above, going from scattered state to some formation of organized clouds, and then they decay in a very non-random manner, where the isolated cells are preferentially suppressing, leading to the most non-random state. And what I show here is, because they only looked at one two-day rain episode, what they found seems to be applicable in general to the overall entire period of the dynamo. And
What's the time scale for those variations?
Oh, I don't know specifically, but this can be happening any time scale. So this could be happening on the actual time scale of each individual MCSs, or it could also be happening on the intraseasonal time scale. And what I want to show is how this evolution actually can be modified by the intraseasonal state. So for example, so this is a repeat of showing the number density and the non-randomness of the convective clusters. So if I just look at the kind of state of the MJO where the number density peaked and form the same diagram, this is what I see. And so this is showing the frequency of currents and those vectors that I defined before on top of it. So what this is showing is that during that state, there's a rapid increase in the number of density and proximity, which then decays somewhat in a reversible manner. However, when I looked at the state of the decayed MJO, it looks slightly different. So what I see here is that when they do increase in number, which does not happen as rapidly as the other phase, it tends to do so in a manner that retains higher proximity more than the other phase. And this in the net then leads to overall higher non-randomness state that is detained during the decaying phase of the MJO. So lastly, what I want to talk about is what might be the environmental factors or mechanisms that lead to the evolution of those following parameters, the parameters that I've talked about, precisely of the number and the non-randomness are evolving with the MJO. So I'm just going to focus on the two environmental factors that are known to influence column organization. The first one is column relative humidity, or sometimes people call it the column saturation fraction. I think they're the same thing. But what I see here is that column relative humidity peaks during the phase of MJO where we saw the highest number density. And this is very consistent with well-known relationship between the tropical rainfall and the column relative humidity. And the other factor that is known to influence column organization is the vertical wind shear. And in this bottom figure, I'm plotting the vertical wind shear defined by different vertical layers. But no matter how the layer that I define, I find all of them to peak during the decaying phase of the MJO where the non-randomness peaked. So this also suggests that adding to the same diagram that I showed before, the role of the shear might have the shear might have a role in preferentially decaying or suppressing the isolated convection, at the same time providing a mechanical support to the formation of new convective cells nearby in existence. So these so far shows that these two environmental factors might have a different mechanism or role associated with the organization on intraseasonal timescale. And we can further look at that by looking at different properties of the convection based on those two environmental factors. So here on the horizontal axis is the column relative humidity increasing to the right, and the vertical axis is the boundary layer shear increasing to the top. And the shading is showing the average number density of deep convective cores conditioned by those two environmental factors. And what you can see that in general, number density increases with column relative humidity. And the next two figures on the right are showing the degree of non-randomness and the nearest neighboring distance. So let's see what these two figures are showing. If I condition this to just look at the environment with high column relative humidity, you don't really see a high sensitivity of non-randomness and the distance to the vertical wind shear. However, if I look at somewhat of a more drier environment, you can see that the non-randomness increases with increasing shear strength, and the distance between them also get closer with the increasing shear strength. So this suggests that within the drier environment, the shear might have a stronger impact on the clustering and non-randomness. So this might be the reason why during the phase of the MJO, when the shear is strong, it can be leading to the increase in the non-randomness of the deep convective cores. So let me summarize what I talked about. So the first message is that the precise definition of cloud organization remains vague, and existing cloud organization indices do not capture consistent interseasonal evolution of cloud organization. So we, as a community, I think we really need to think about what we mean by cloud organization in order to help our understanding of cloud organization itself, because we need to know what it means if we want to understand how it happens. The second point is that because I didn't learn much by looking at cloud organization, my work looked at how convective clouds actually evolve with the MJO by examining the parameters that goes into the cloud organization indices. And here's what I found. So during the suppressed phase of the MJO, there's a low number of more randomly scattered convection. And as the environmental humidity increases, the number of convective cells increases, and that naturally leads to their higher proximity. And higher proximity means that the potential for them to merger is higher, leading to formation of larger convective systems that grow in size and leads to the formation of stratiform ring. Then as the environment dries, the convective cell decays in a very non-random manner that seems to be supported. What we hypothesize must be supported by the vertical ridge shear. And that's all I have. Thank you for your attention.
So I'm curious as to, since you found that the other indices don't work well for the MJO, but I would imagine whenever they were developing, they worked for whatever examples those authors were looking at. What do you think is different about the MJO versus, organized convection elsewhere that may have worked well for those indices versus this?
So from my understanding, I think the development of especially the self-aggregation based indices were not motivated by, as you said. So what they did is they defined those organization or self-aggregation indices based on what they see in idealized simulation. So they define those indices and then apply to the observation to see if the observation shows consistent story from their idealized simulation, which could be misinterpreted, I think, because, for example, I think a common finding is that they find that in idealized simulation, when things are getting more aggregated, they find the overall environment domain to be more dry. And they say that application of their indices finds the consistent story in observation. But what's actually happened in observation is that what they define as more aggregated state is capturing the suppressed state of the observation. So therefore, that should be associated with the drier environment. But I think it should not be interpreted the same as the results from idealized simulation.
So it's got implications for the arguments that people are making.
Like I was just saying, like
Yeah, a lot of-
Sky and iORG and all those like use satellite data, like to try to do this. But when you actually apply this to such high resolution radar data, you pick up so much more information.
Yeah.
Yeah.
So yeah, it's very highly sensitive to the variable, the resolution, what data set you use. So.
The idealized simulations all have the same amount of rainfall too, right? So an idealized simulation is in radiative convective equilibrium. So that's kind of the situation that they're thinking of. So controlling for the rainfall, maybe IOR or these various things work. Yeah, that would be good.
So, I have a million questions for you, but we'll talk more after. So, one of the interesting things about when we applied iORG to the 2-day events, right? Like, it kind of didn't work for all of them, like all the 2-day rate events that were embedded within the active period. And my question for you then, the 3 different MJO events had quite different environmental conditions. The October and November ones were much weaker shear, where it was like this embedded convection within very widespread stratiform, where December had just ramped up westerly winds with squall lines with not as much stratiform. So my question for you is, based on this finding, like that composites all of it, how do you think which variables go into this metric and how you compare it to the environment might vary if you were to separate out like October, November versus December as an example. Do you think it would be sensitive to that, I guess, since they were so different?
I'm not so aware of how the environment varied between those three events, but that would be interesting, kind of using the same kind of diagnostic framework to compare the three events.
Yeah.
Might be an interesting idea. But my objective here is to kind of get a bulk statistic on what tends to happen. And the differences between those three events will be interesting. But from large scale person, you might say it's a noise. I know, but
No, so I guess to follow up then, so do you think it's not very sensitive to the coverage of stratiform? Because that's one of the consequences of the differences between those three cases, was that the coverage of stratiform was so drastically different. Do you think that would have much of an impact on this based on the different components you looked at, or is that what you mean by that's kind of all in the noise?
I don't know the answer to your question. I think that would be something interesting to test. If the stratiform itself has an impact on this kind of organization of deep convective cells, right, then we should see some sensitivity.
Were you using the convective, your N's and your NDDs? Were those just convective regions?
Yes,
or
just deep
deep convective regions?
So like there was so much more convective versus stratiform like relative contributions, so that's why I was kind of curious how much it mattered or not at all, and that's really interesting.
Mm-hmm.
Yeah.
I have a question, but we usually try to answer our student questions first, so I'm just wondering if any of the students have questions.
I have a question that you may not be able to answer. I'm not exactly sure. I'll just go ahead and ask it. But I know that the theory of convective aggregation, some of it lies in the fact that there's a change in sea surface temperature over time, or the warming of sea surface temperature that can lead to more of this clustering, increased rainbow cloud. And I'm just wondering how you might try to understand the role that a change in sea surface temperature can play in the development of MJO in this sort of non-randomized.
From the observation, it would be hard to strictly kind of separate the effect of SST, because the changing SST is kind of embedded all in with the changes in intraseasonal timescale. But again, I think that the idealized kind of simulation of the self-aggregation is a very powerful tool for understanding some of the processes, but I think applying to the observation is just very challenging. Yes.
I had kind of a simple question, but just looking at the schematic had me thinking, I was just wondering how difficult it is to observe whether or not you have like multiple smaller cores or one larger core, and like can you do that from satellite data like remote sensing, or do you have to be like in situ to be able to tell? I don't know much about how to.
The size is what you're wondering about?
Yeah, because like the distance between these cores seemed important for what you were doing, but
Oh, yes.
I'm not sure how easy it is to actually tell whether or not you have many or one when they're close together like these.
Many or one?
Just kind of wondering about separating out individual cores. You're using radar data.
Yeah, I'm
right?
using
so
radar
it might
data,
be different
so,
with satellite data.
Right, so satellite data will be difficult to separate those convective cores, so that's why the radar has an advantage of being able to separate them. I did apply all this cloud organization indices to the satellite data as well, and I think that's even harder to interpret because some of the metrics are intended to apply to updrafts or convective cores, and the satellite data just does not allow us to do that.
Oh, thank you.
Go ahead.
I'm wondering about the shear impacts. So basically you're showing that when you have a drier environment, the shear is having a bigger impact.
Mm-hmm.
Do you think that's like just a question of ventilation? Like the shear is blowing dry air into the small systems? Or how are you thinking about that explaining that mechanistically?
I'm kind of more thinking about, so the shear is defined in the multiple layers, and I think ventilation, I think you're thinking more of the deep layer shear.
Yeah.
But what I was showing is the boundary layer shear. So what I was thinking more about kind of the shear and the interaction of the horizontal vorticity associated with the cold pool, kind of leading
Okay.
to the formation of new convection. And I think when I looked at that, I think I also looked at the deep layer shear, and that has less sensitivity with the kind of clustering and non-randomness. So the boundary layer seems to be more playing an important role.
Interesting.
My attention is drawn to, I love the sort of elegant analysis of geometric entities and in space and all that. It's one of the things that fascinates me. So this was really exciting. But my attention is drawn to these organized convective pools that occur on the west side of upper troughs off the Pacific Northwest coast, for instance, when you have a really cold air at 500 millibars. I know there's nothing similar about the way they get organized, but I wonder if some of these metrics that you've developed, in addition to what was already existing, would really apply in some of those cases, nearest neighbor, and it would tell you something about those environments. And then what do you think about the chance that what you learned from studying a system that's less mysterious, because that's mostly stability driven, and the organization then maybe is something that catapults off of that, might tell you about what's going on in the MJO? Because I don't know very much about the MJO, but one of the things that's mysterious to me is how do you get huge areas of dry air to mysteriously appear and stop to suppress the convection? If that's the mechanism that suppresses it, is it not just gentle subsidence and then you have a wave phenomena or something else? I mean, how do you think you might be able to pull insight from the mid-latitudes in a simpler system to apply here using your really cool metrics?
So the metrics, I think I just want to clarify that I don't advocate for using these metrics. Maybe what you mean, the organization, especially what I mean is organization indices. I don't advocate for using that.
Yeah.
Just because it's so hard to learn actually what's actually going on. But then actually looking at the parameters that go into the organization indices, such as the distances and the number of sites, could be applicable, could be used for the mid-latitude system. And then, over the continent of the US, you have plenty of radar data. So I'm sure someone is working on that I might not be aware of, but you might not know. And I don't know how we can compare the dynamics of a system in the mid-latitude versus the tropics, because the dynamics is so different. One fundamentally is the temperature gradient is pretty non-existent in the tropics.
Yeah.
Where
these interesting aggregate convective clusters on underneath cold pools aloft don't really have a strong temperature contrast aspect to them. Okay. It's just a stability reduction. And it makes me wonder if there isn't something you can pull out of that. Because the dynamics are so simple as to be almost non-existent, and so the differences might not be as big as you think.
What do you mean by stability reduction, Tom?
If you get minus 35 degrees at 500 millibars over the Pacific Ocean, that's plus 10, you get a super adiabatic lapse rate, or at least a 9-degree per kilometer lapse rate. But the air is moist, so it's absolutely unstable. And that's why you get these convective outbreaks. And then they space themselves based on how unstable it is, because that tells you how strong the updrafts are and how much the compensating downdraft has to occupy space and all that. So I'm just wondering if you apply some of these neat geometric extensions that you've done to such a simple case as that in the mid-latitudes, knowing what is probably driving that convective aggregation, can you learn anything about what might do some things down here?
Yeah, that would be, so any of your students here? Perfect project for you. Yeah,
Anyway.
because that would be, interesting to think about how we can pull.
So there's theories for how far these updrafts are apart
Just in my
the
head.
mid-latitudes?
You can tell when you look at
okay.
a satellite picture, if they're far apart, it's colder. If they're close together, it's not as cold because the stability is not as weak. Yeah, you can tell. I make a guess every Friday, and I'm usually within a degree.
Oh, okay.
So, but that's without, AI, just regular eye.
Yeah, so I just wanted to see if you can comment on one of the last clusters you showed, which was really interesting in that you didn't see any particularly major changes in like convection number and density or separation when you have like a really humid environment in the enhanced phase, but that you see something that was, okay. Something.
One of the aliens are called.
Yeah, the aliens are coming or something. But when you had like a more, like in the decaying phase, you did say something that seemed a lot more systematic. And I'm wondering if you could comment on, like, I'm kind of like thinking here as in like, is the environment in the enhanced phase so favorable because it's so humid that convection kind of just goes trigger happy and it just doesn't kind of care that much?
I think that's what I'm thinking, that when the, I don't know.
That's not you, it's upstairs.
Oh, okay. So
Yeah.
what I'm thinking is that when when there's an environment with such a high column levels of humidity, that convection are so easy to trigger in both random and cluster manner. So they just randomly form, or not necessarily all random, but they form so easily. And when the number increases, that naturally leads to higher proximity of them. But during the kind of a drier event, they really need additional support to form.
Yeah.
And which could be through kind of moist patches that's already existing within nearby the existing convection, or its interaction with the vertical shear that leads to the formation of the new one nearby. And I think that's why it has a bigger impact on the non-randomness.
When Larissa was asking about the physical mechanism, you talked about, particularly between enhanced decaying, how now you have cold pools and the shear is interacting with the cold pools leading to this decay. But there's also, the shear is only in that enhanced decaying phase too, right? So what makes the shear?
What do you mean it's only, so the value peak?
Yeah,
but-
the figure a couple back showed, the relative humidity was highest, that's one further back. Sorry. Yeah, right there. So the vertical wind shear is in that enhanced to suppressed stage too. And that's when there's cold pools. How does that vertical wind shear get formed in the enhanced phase, I guess?
Oh, okay. What leads to the peak
Yeah,
of this?
yeah.
This is associated with the formation of the low level kind of overturning circulation associated with the Madden-Julian Oscillation. And so the background state, I think here is the, over the Indian Ocean is the westerly. And then at this phase of the MJO, it kind of adds to the speed of that, and so that leads to greater shear in the mountain.
Okay, thank you.
I think I probably needs to start heading out. My flight is out.
Yeah, so, all right, everybody, thank you for coming.
Thank you.
Thank you.